Hi everyone, today we are going to present our project 4242, where we explore the potential of machine learning in sports analytics, specifically in predicting NBA championship. Firstly, I would like to discuss the motivation behind our project. The main goal for our study is to predict playoff outcomes based on the performance observed during the regular season. Additionally, we aim to analyze the key factors that contribute to winning the NBA championship, and by identifying these factors, we can enhance the predictive power of our model and provide insights into make the championship winning team. Finally, dealing with unbalanced data is a common challenge in sports analytics. We're employing appropriate predictive models that are specifically designed to handle such unbalanced data situation.
And now I will introduce the source of our data. We manually scrape data from Basketball Reference website. After exploring the relevant sections of the website, we download data from 2000 to 2022 seasons. We can capture game-specific information for both the team and its opponent. After extraction, the data were cleaned and transformed, where each entry is labeled with a year and the championship team for each section. Season is marked with a champion label. The data then is organized so that each team's statistics include both the team and opponent metrics in the same row, but separated into different columns with opponent-related data prefixed with an O. This allowed for direct comparisons between team and opponent metrics in a unified view. Finally, the structured data were exported in a format like CSV, ensuring that it was ready for analysis with organized information. Here are the columns in our dataset. For each season, the league contains 30 teams, adding up to 686 rows of data points, each with a non-null value to all independent variables. Based on the 70% training set and 30% testing set convention, we set the training set as all data points from 2000 to 2015, and the testing set as all data points from 2016 to 2022. Each row contains 50 columns, including 4 columns of champion, team, and year, and how many star players included in All-Star. Both the home and opponent data have 23 columns each. The columns for the opponent data are prefixed with an O. Table in this slide shows 11 columns of home data. And the table in this slide shows the other 12 columns in our dataset. Statistics in the table are fundamental to analyzing player performance and team. These statistics are vital for player scouting, game planning, and performance evaluation in the NBA.
At this stage, we have utilized the two different machine learning models. Firstly, let's take a closer look at our OC curve display here. This is from our first model, balanced random forest, because it has capability to handle unbalanced datasets. Our models are OC curve, represented by the red line, shows a steep ascent in the true positive rate with minimal increase in the false positive rate. This steep ascent and subsequent plateau and a high level of true positives with very few false positives illustrates the model's robust discriminative ability. It is particularly effective in minimizing both type 1 and type 2 errors, which are respectively the incorrect rejection of a true positive hypothesis and the failure to reject a false hypothesis. Such a profile indicates that balanced random forest is not only capable of distinguishing between the classes effectively, but also maintains its discriminative power across various thresholds. For the second model, we utilize the card. On the left, you can see the decision tree structure for our card model. Each node in this tree represents a decision point based on the values of certain predictors. Now, moving to the right side of the slide, we have the confusion matrix of our card model. The key takeaway from this matrix is that our model achieved an overall accuracy of 96%. This high level of accuracy suggests that current model is highly conservative, focusing on minimizing false positives. However, this comes at the expense of potentially missing all positives cases, as evidenced by the false negatives observed. That's all our work so far. In the following week, we will keep doing feature engineering and try to fine-tune our model. Thank you.